Vienna, who spent the previous 2 years at the University of Toronto, and he's going to tell us about Lorentzian length spaces.
Thank you very much. Thanks to the organizers, Christina, Gasar, Robert, and Matthias for inviting me to this seminar, and also thanks to the organizers of the program. I think this will be a really great program. Looking forward to the next weeks. So I will talk about Lorentzian length spaces. This is an approach to Lorentzian geometry we developed, where we don't want to have a smooth structure and still want to make sense of causality and curvature. So why do we want a synthetic approach to Lorentzian geometry? So first, there is the PD point of view on the one hand. So you write Einstein equations as a hyperbolic PDE, then you have a very sophisticated solution theory and might get some solution in some Sobolev space, which might not be smooth enough, but you still want to make sense of the resulting geometry and causality of the space-time. On the other hand, there are physically relevant models of space-times where the metric is of low regularity. For example, matched space-times, where you match together regions with different matter content, and if this matter distribution is discontinuous, say for example on the surface of a star, then via the Einstein equations you know that the metric cannot be C2. However, there are even exact solutions of lower regularity, for example shock waves or impulsive gravitational waves. Impulsive gravitational waves in one form have a Lipschitz continuous metric. On the other hand, there's another form which even has a distribution, but still they are physically relevant exact solutions of the Einstein equation. One other goal of us was to separate main concepts and derived notions. So what is fundamental, what can be derived for the causal structure. And also for us, a main example are spacetimes with continuous metrics. So they might not be differentiable anywhere, but still you can talk about the causality, and we wanted to have a way to define curvature bounds for spacetimes with continuous metrics. Connected to that is that this then allows you actually to also define curvature bounds without having even a Lorentzian metric. And this is connected to possible applications to quantum gravity, because there you might not have a Lorentzian metric. For example, there's causal set theory or causal Fermi systems or other approaches where you don't have a Lorentzian metric. And let me just mention that the regularity class where the causality theory is completely fine is C11. So the metric is differentiable and the first derivative is local Lipschitz continuous. Then the causality theory is fine. You have local uniqueness of geodesics, and you can define still curvature as an L infinity function. And also let me mention there is a complementary approach to ours by Christina Saemann and Carlos Vega, who define what's called null distance on spacetimes. So their approach is that you have a nice enough time function, then you can define a null distance, and then you actually really have a metric in the sense of a metric space. For us, the approach is complementary. We say, okay, we don't have a metric, so what can we formulate just in terms of the causal structure and the time separation function? And let's go first back to the Riemannian case. So a smooth Riemannian manifold has sectional curvature bounded below by K. Doesn't work. Okay. Has curvature bounded below by K if for all small enough geodesic triangles, and you take 2 points PQ on the sides of the triangle, and then you take a comparison triangle, so a triangle in constant curvature space K, two-dimensional constant curvature space K. You take a comparison triangle, look at the distance there of the corresponding points, and if this bounds the distance in your space PQ below and in your manifold from below, and this holds for all small enough triangles and for all points on the sides, then it has sectional curvature bounded below by K. Same thing for curvature bounded above. And for a semi-Riemann manifold, especially for a Lorentzian manifold, it has been for a long time thought that there is no notion of curvature bounds, but this is not true. You just have to be more careful. So a smooth semi-Riemann manifold has sectional curvature bound below by K if space-like sectional curvatures are bound below by K and time-like sectional curvatures are bound above by K. So you have to flip the sign. It depends on the causal character of the tangent plane you look at. And same thing for the curvature, for the inequalities flipped. And then Alexander and Bishop showed that you can actually characterize curvature bounds via triangle comparison in smooth semi-Riemann manifolds. So a smooth semi-Riemann manifold has sectional curvature bound below by k in this sense here. If for all geodesic triangles small enough, PQ points on the sides, and now you look at the signed distance. So the signed distance is the length of the shortest geodesic connecting these 2 points. So this is a smooth semi-manifold. So locally you always have geodesic connecting 2 points. And then if the geodesic is space-like, then this will be it will be positive. If it's null, this will be 0. And if it's time-like, it will be negative. And this is what they call the signed distance. And then this actually characterizes these sectional curvature bounds. So, and in the metric case, of course, this definition, this Toponogov theorem, gave rise to Alexandrov spaces, because this kind of curvature bound you can define for a metric space. As long as you have a metric, you can define this triangle comparison. And this gave rise to really a rich theory, Alexandrov spaces, cat K spaces, and so on. But how to generalize this signed distance here in the semi-Riemannian case, especially the Lorentzian case? So what to do there? And our approach is that we take the time separation function instead of that, and we will see that this works out. But let me just first. So this, the time separation function is minus the signed distance if the points are causally related. Yes, yeah. So let me just briefly review Lorentzian causality in smooth spacetime. So Mg is a smooth connected manifold, and G is a Lorentzian metric, meaning that it has a symmetric non-degenerate 0,2 tensor, which has signature minus plus plus plus. I know some people used different conventions, but this is what I will use. And usually G is smooth, but G could also be just continuous, for example. Then you can characterize tangent vectors. A tangent vector is time-like if the inner product with itself, with respect to the metric, is negative. It's null if the inner product is 0, but the vector is not 0. It's causal if the inner product is non-negative and non-positive, the vector is non-zero, and space-like otherwise. Then you can define this, of course, analogously for curves into M, saying that the tangent vector has to satisfy this almost everywhere, or everywhere, depending on the regularity of the curve. And then you can define the length with respect to the metric, which is just to integrate the absolute value of the square root of the norm. And now a space-time is a Lorentzian manifold which can be time-oriented. So you have a consistent way of choosing future and past. So there exists a time-like vector field T, and then with respect to this vector field, you can define that a tangent vector V is future-directed if the inner product with V and the vector field is negative. And analogously, you can define this for the curves. And then we can define the causal relation. So we say that P is less Q. P is time-like related to Q if there is a future-directed time-like curve from P to Q. And we set I plus of P as the chronological future of P as all points Q, which are in the chronological future of P, similar I minus of P. Also, we say that P is lesser equal than Q if there is a future-directed causal curve from P to Q, or they're equal. And similarly, define J plus of P as the all Q which are in the causal future of P. So this is the causal relation. And this motivates our definition. This is an analogy of what is a metric space. For the Alexandrov space is what we call Lorentzian pre-length space. And so here X is a set. You have a lesser equal a pre-order on X. So this is transitive and symmetric. And a transitive relation less, it's a time-like relation, which is contained in lesser equal, meaning that if 2 points X is less Y, then also X is lesser equal Y. We put some metric D on X, so really metric space metric to just have some metric topology on the set X. And the tau, a function from X times X into 0 infinity, which is lower semi-continuous with respect to this D. And then we call this a Lorentzian pre-length space if tau satisfies the reverse triangle inequality. So tau xz is greater or equal to tau xy plus tau yz for all triple of points x, y, and z that are causally related in this order. And has the property that this is zero if and only if they are not, if this is zero if this is they are not causal related, and positive if and only if they are time lag related. And this tau is called the time separation function. For example, Robert in his talk had the other convention that he sets tau to minus infinity if they are not causally related and zero if they're causally related. This has the advantage of encoding everything in the time separation function, and I slowly get to appreciate this convention. But this, of course, is in analogy with the space-time case, and somehow it's equivalent. If you have this convention, you can always go back and define your time lag relation. And then in that order, for example. Okay, so a first example is, of course, a smooth space-time, which the usual time separation function tau pq is the supremum of the g lengths of all future-directed causal curves from p to q, or zero if there are no causal curves.
So may I ask, why do you need two relations like this, less than or equal and less isn't like the change of the closure of the eye or something?
No, that's not always the case. So this really is like a causality condition that the less so less or equal is the closure of less is not always true. Yeah, this is not true. Yeah. Yeah, so locally you would like to have that always, but globally this even is non-true. I think. Yeah, I mean, but even for smooth space-times, this is not true. So I think if it's globally hyperbolic and causally simple, which are like the top causality condition, then it's probably true, but below that, I think it's not true. So for example, you could always think that you have like Minkowski space and you look at the light and you delete one point, then the light comes from this point, where the null geodesic would have gone through this point, then the closure of less would contain this part here, but which is not contained in lesser equal. So maybe I can draw it. It's maybe better. So one sees that at home. Maybe someone can turn the camera.
So I think this is monitoring.
Okay.
Let's see. It's a new camera system.
Okay, I see. So if you have a point here, and you have I plus of, and then you delete the point here, then this part here, this will not be part of the closure. Sorry, this will not be part of J plus of P. So this here is not contained in J plus of P, but is in the closure of I plus of P. And this, yeah.
J plus is which one? Less than or equal?
J plus is less or equal.
Less than or equal.
Yeah.
And I plus is the double less
yes.
sign.
Yeah.
And
yes. Another example is you can, for example, look at finite directed graphs. You can also view that as Lorentzian pre-length spaces. Then you can define what is a causal curve. A curve is then a curve which is totally ordered by less or equal, a time-lag curve which is totally ordered by less. And you can define their length by summing up the time separation of polygons. You can define causality conditions, and you can define maximal causal curves, which are tau distance realizers. So these are curves whose length is exactly the time separation of the endpoints. And this is like the analogous thing to geodesics. Yes? Yeah. No. Actually, you could, everything I said here, you could do without the D. I haven't used it yet, but my definition of causal curves is that they are local Lipschitz continuous with respect to this D, because then you have limit curve theorems. But in principle, you could do also without that. Yes, because so you need that it's proper, or everything is in a compact set. These are like the two cases we are doing. You can, yeah, it's locally complete. Yeah. Because these are the only two cases we actually need the limit curve theorems. Yeah. And in a sense, this is some kind of background metric. So any metric which is Lipschitz equivalent will give you the same curves, Lipschitz curve. But of course, you can also forget about D, do everything like that. You can even define a topology, the Alexandrov topology, just by using tau. Yeah, so, and this is just the axioms we came up, but of course you can sometimes have to change them for some applications. But the main idea is that you can formulate enough of the theory in terms of the causality and the time separation function to make really, to be really useful. And for some application, it might be useful to forget about the T and maybe you just use the Alexandrov topology and continuous causal curves, for example. Then you lose the limit curve theorem, but maybe you don't need it at this point. Okay, so then a Lorentzian length space is, apart from some technicalities, for example, that locally this causal relation is closed, not necessarily the closure of less, but this is closed, that you have enough causal curves, and that it's localizable, meaning that you have nice enough neighborhoods where you actually, the causality is nicer and you have existence of local geodesics. Then it's called a Lorentzian length space if tau is intrinsic, in the sense that the tau you started off with is actually given as the supremum of the tau lengths of all future directed causal curves from X to Y, or 0 if they are known. Then you can also say what it means to be regular. So if locally maximal causal curves have a causal character, so they're either null or time-like, then it's called a regular Lorentzian length space. And again, a first example is a smooth spacetime, smooth and strongly causal spacetime. Then you can actually show that this tau length is actually the G length. And the funny thing is, for example, Penrose always used this tau length, but of course it didn't call it like that, but it just, when he defines the length of a causal curve, he summing up what he calls trips, which are the short geodesics, but then he never ever shows that this gives you the usual length. And it's actually non-trivial to show that this is the same. And then what you get here is then actually a regular Lorentzian length space. And our main application was to continuous spacetimes. So if you continuous spacetime, which is strongly causal and causally plane. So sorry, I didn't explain strongly causal. So this means that there are no almost closed causal curves. So if you have two, there is no sequence of curves where the endpoints converge to each other. In particular, there is no closed causal curve, but also no causal curve, no sequence of causal curves where the endpoints converge. And it's causally plane, meaning that there are no causal bubbles. This was the phenomenon found by Kruschel and Grant for Hölder continuous metrics. Then the Lorentzian pre-length space is actually Lorentzian length space for the continuous metric. It might not be regular because the causal maximizers need not have a causal character, but it's still intrinsic in this sense. Sorry? What the causal bubble is? Yes, I can show that again. So this is an example of a Hölder metric, and you have this. So here you have I plus of 0. And then here, actually, you can go null here and then branch off at any time. So everything here is J plus of 0, but this is I plus of 0. So in particular, the boundary of I plus really has a positive measure. So the difference of, yeah. 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 And this is for Hölder continuous. And this you have to rule out because then push up does not hold. Sorry. No, this is in the tau is here. The tau is oh sorry. The tau is positive if and only if they are time-like related. This is somehow encoded here, the push-up. Yes, and again, for example, what I said, well, maybe you want an application where you can also talk about these bubbling spacetimes, then you would have to drop push-up from your axioms and see what you can do then. But for us, we assume that we have the push-up property. Okay, so let me mention just some things which have been done for these Lorentzian length spaces. So we studied some of the causality conditions, and then Akihao, Cabrera, Pacheco, and Solis actually established the more or less full causal ladder holds. So we start with global hyperbolicity, which implies causal simplicity, which means that less equal is closed, and so on. Then we have introduced time-like causal sectional curvature bounds via triangle comparison. We applied this to the question of inextendability of spacetimes and related this to a curvature blow-up. Also, we started a large class of examples, which is called generalized cones, and had a first synthetic singularity theorem. Then there are these time-like Ricci curvature bounds, building on work of Robert. Cavaletti and Mondino introduced time-like Ricci curvature bounds in the synthetic sense, and then Matthias introduced some other conditions, which is analogous to conditions in the metric measure case. Then Mondino-Sur gave a synthetic version of the Einstein equations, basically saying that you have time-like Ricci curvature bounded below by lambda and curvature bounded above by lambda. Then, surprisingly, there is some application to contact geometry. Then there is also a connection between the null distance and these Lorentzian length spaces. So you can define this null distance on Lorentzian length spaces if you have a nice enough time function, and somehow this approach is compatible. Connected to that, Butcher and Garcia-Havlik introduced time functions on Lorentzian pre-length spaces and showed that this existence of a Cauchy time function, for example, is equivalent to global hyperbolicity, as in the smooth case. Then Robert talked a bit about that 3 weeks ago. We introduced canonical measures on Lorentzian pre-length spaces, which are analogous to the Hausdorff measures, and therefore you can also define Hausdorff dimension, a kind of dimension for such spaces. Also, important construction in metric geometry is gluing of spaces, and two colleagues, Tobias Behren and Felix Rott, did that recently. And finally, we introduced angles and angle comparison into this sphere, which again in metric geometry is really an indispensable tool. Also, more or less simultaneously, Barrera, De Oca, and Solis had a similar approach. And I will, in this talk, focus on the curvature bounds via triangle comparison, briefly outline this application to inextendability of spacetimes, tell you about the generalized cones and the hyperbolic angles. Okay, so how can we do this triangle comparison? So a time-like geodesic triangle is a triple XYZ. We denote this by just triangle XYZ, such that they are time-like related, and the time separation of X and Z is finite, and the sides are realized by future-directed causal curves, meaning that there exists future-directed causal curves alpha, beta, gamma, such that the tau length of alpha realizes the distance from X to Y, beta realizes the distance from Y to Z. Sorry. And gamma realizes the distance from X to Z, and then by that reverse triangle inequality, actually the other sides are finite, and these alpha beta are maximal, so they are like geodesics. So you can picture this like here. You have your points X, Y, Z in your space. You realize that the sides by these curves, the points are time-like related. And what you can do now is then you can realize this if the side lengths are small enough, depending on K. You can realize this in a space of constant curvature K, the space MK. And these are the so-called Lorentzian model spaces of constant curvature. So K is a real parameter. And the MK is then, for K positive, is the simply connected covering manifold of the two-dimensional Lorentzian pseudosphere. If K is 1, this is just de Sitter. Then if K is 0, this is just two-dimensional Minkowski space. And if K is negative, then this is again a simply connected covering of the two-dimensional pseudo-hyperbolic space. And if K is -1, this is anti-de Sitter. So you look at triangles in these spaces and compare then the time separations of corresponding points. And Harris and Alexander Bishop showed that there is actually, as if the side lengths are small enough, again depending on k, then there is a unique, up to an isometry of the model space, time-like triangle in MK, which realizes these distances, and of course the causal relations, because otherwise there cannot be a triangle with the same side lengths. So the curvature bound then looks like this. A pre-length space X has time-like curvature bounded below by K. If for all points in X you have a neighborhood U called comparison neighborhood or K comparison neighborhood. If tau is finite and continuous on this neighborhood, and for any 2 points X, Y, and U, which are time-like related, there exists a future-directed maximal causal curve in U from X to Y. So these first 2 points are just that you can actually compare something. And then the comparison is that for all small enough time-like triangles X, Y, Z in U, there is a comparison triangle in X bar, Y bar, Z bar in the constant curvature space MK. And you take 2 points PQ on the sides of your triangle, and P bar, Q bar corresponding points in the comparison triangle. Then for curvature bounded below, you actually have that the time separation function is bounded above by the time separation in the model space. So this is the other way around as in the metric case. And of course, and the same thing as if you have curvature bounded above, then again the inequality flips and you have that this is bounded below by the time separation in the model space. And by work of Alexander Bishop, you know that smooth Lorentzian manifolds with sectional curvature bounds, as I defined at the beginning, are examples of spaces which have this kind of curvature bound. So in metric geometry, Alexandrov spaces have curvature. Sorry, is the question? No, because their characterization is the full sectional curvature bound. So they also includes the space-like part, which for us we don't. So if it satisfies in the Alexander Bishop sense the sectional curvature bound, then it applies the triangle comparison, but not the other way around. So, sorry again. So in Alexandrov spaces, geodesics do not branch. So if you have curvature bounded below, and the same holds for pre-length spaces with time-like curvature bounded below. So let me draw that again. So what we mean by a branching point is that you have a time-like curve, and then you have it continues in two parts, where each of the parts viewed separately is a maximal time-like curve between this point and this point and this point and this point. And then you would call this a branching point or this a branching point. And if the curvature is bounded below, then this cannot happen actually. But let me give an example where this does happen for a Lorentzian pre-length space. And this is what we called a time-like funnel. So you take, say, Minkowski space and take a time-like curve in Minkowski space from P to Q, and then look at I plus of Q, I minus of P, and X is then, so say this is gamma, then X is I minus of P, gamma, and I plus of Q. This is your whole space. Then any curve, and you can show that this is actually a Lorentzian length space, then any curve from, say, X here to Y here has a branching point because it has to go through this point here. And so this tells you that this cannot have curvature bounded below. So we showed that a strongly causal Lorentzian pre-length space which has time-like curvature bounded below, then time-like geodesics have no branching point. So by using this triangle comparison, you can show that this cannot happen, this branching. Also, you can, of course, then say, if you have this curvature bounds, you can say that if space has a curvature singularity in the synthetic sense, if for every k there is a point, sorry, and a neighborhood u, such that you can actually do the comparison in your neighborhood. So tau is finite and continuous, you have maximal geodesics. But this triangle comparison fails for this k. So for every k, you have a point in the neighborhood where you can do the comparison, but the comparison fails, then you say it has a curvature singularity. And you can actually show that Schwarzschild, the interior singularity, is a curvature singularity. This does not have curvature bounded below by just looking at the geodesics. So this.
Sorry, can I ask a question? Well,
yes.
So is there I think, let's say for curvature bounded below, is there a globalization theorem?
A globalization theorem? Not yet, but actually colleagues are working on that.
Okay, so it's expected there should be one.
Yes, I think so, yeah.
And for curvature bounded above, let's say, in simply connected case, or something like Hadamar's theorem.
Yes, I think it's connected there with gluing, if I remember correctly. So if the colleagues are looking at that.
Okay, but
I don't remember the details.
But it's not known yet.
No, it's not known yet.
And there are no like obvious counterexamples.
No, also not yet. No.
Okay.
So it's still the hope that this works. Yeah.
What is globalization theory?
So that if your space has these comparison neighborhoods, every point has one, that then actually you can do the comparison globally if you're using large triangles, yes.
But you don't have anything that is simple.
Yeah, and so let me think about what exactly the yes, exactly. And I'm not sure if the causality makes it worse or is it as difficult as in the metric case? I don't know. Okay, so then we can apply this to the question of inextendability of spacetimes. So this is a fundamental question in relativity. When is a spacetime maximal? When can you not embed it isometrically into a larger one? This is connected to the definition of singularity in general relativity. For example, Penrose defines a singularity as the existence of an incomplete causal geodesic. But if you take just Minkowski space, delete again a point, then there is an incomplete geodesic. So it's singular in that sense, even though you know it's not really singular. And it's not singular in another sense, meaning that it's not maximal, because you just give again at the point, so you embed it into the larger one properly, isometrically. So you knew it was not really singular. And this is therefore an important question: when is a spacetime maximal? And for example, if a spacetime is a smooth spacetime is time-like geodesically complete, then it cannot be extended by a C2 manifold, Lorentzian manifold, because this would contradict the geodesic completeness. And recently there was this fundamental result by Spirsky, who showed that Schwarzschild is actually inextendable as a C0 manifold. So you cannot actually embed it into a spacetime with continuous metric. There you cannot use make-of geodesics, but he was still able to show that it cannot extend it continuously. And our proof is more along the lines of the argument using geodesics, because our setting allows to have a notion of geodesic. So a strongly causal Lorentzian length space is like the analogous or the sufficient criterion for time-like geodesic completeness is that all inextendable time-like geodesics have infinite tall length. Then it's inextendable as a regular Lorentzian length space. So it might be extendable as a Lorentzian length space, but the extension cannot be regular, meaning there will be maximal causal curves which have a null segment and a time-like segment. And of course, you can apply this then to the setting where your original object you wanted to extend is actually a strongly causal smooth, a time-like geodesically complete space-time. Then this again is inextendable as a regular Lorentzian length space, meaning you cannot extend it as a, so you not only can you not extend it as a space-time, but also you cannot extend it as a regular Lorentzian length space, which might not be even a manifold, for example. And this is then related, this being non-regular is related to curvature unbounded. And this was the first time to have a connection between curvature blow-up and inextendability. So this concludes this part, and we come now to the generalized cones. This is joint work with Stephanie Alexander, Melanie Graf, and Michael Kunzinger. And this gives us a huge class of examples of Lorentzian length spaces. So this is, we take a metric space XD, an open interval I and R, and a continuous positive function F. Then we call this product here, Y, I times Fx, a generalized cone, a warp product with one-dimensional base, and F is the warping function. So warp products are important in differential geometry. They have a nice structure and easy examples. However, in our case, we need a one-dimensional base because otherwise we don't know yet how to define the causal structure. And this works as follows. You take gamma, a curve, absolutely continuous curve, into your generalized cone, which has the components alpha, beta. So alpha goes from J into I and beta goes from J into X. And then both alpha, beta are absolutely continuous, and the derivative of alpha exists almost everywhere, and the metric derivative V beta of beta exists almost everywhere. The metric derivative is just that you take the limit of the distance of beta t plus s, beta t, divided by the absolute value of s, and this actually, you can use the metric derivative to calculate the length of beta. So if you just integrate the metric derivative, you get the length. Then you can define a causal structure as follows. For such a curve gamma with components alpha, beta, you say that this is time-like if this quantity here is negative, so minus the derivative of alpha squared plus f composed alpha squared, metric derivative of beta squared. It's null if this is 0, it's causal if it's non-positive, and it's future directed if alpha dot is positive almost everywhere, or past directed if alpha dot is negative almost everywhere. Then you can define the length of a causal curve as just minus this quantity square root and integrated. And for this talk, X will be a locally compact geodesic length space. But this construction so far works for any metric space. Then you can define the causal relations and I plus and J plus as usual, less if there is a future directed time-like curve from X to Y and so on. And these generalized cones have really nice properties. So for example, if you take gamma, a future directed causal curve, which is maximizing, then the fiber component beta is a minimizing geodesic in a metric space XD. And the converse does not hold. It's so that if beta is minimizing, then gamma need not be maximizing because you need the right parameterization of alpha for that. What is true is the fiber independence. So the base component alpha depends only on the length of beta. So in particular, it's independent of the curve and the metric space otherwise. Meaning that if you take another metric space x prime d prime and a minimizing curve beta prime, which has the same length as beta and the same metric derivative, then gamma prime, defined as alpha beta prime, is maximizing causal or time-like, depending what gamma was, in the generalized cone over x prime. So what this implies is that if you have 2 points P and Q, which have the components P0, P bar, Q0, Q bar, The time separation of PQ depends only on P0, Q0, and the distance of P bar, Q bar in X, and of course on F. So we already talked about the bubbling and push up. So this does not hold in low regularity necessarily. Also, the question if the chronological future of a point is open does not hold necessarily. However, these generalized cones have such a nice causal structure that this always holds. And you can do that as follows. So given P0, you study the ODE. Derivative of H is F composed with H with this initial condition. So F is just continuous, so you cannot use the usual solution theory, but it's a one-dimensional ODE with continuous positive right-hand side. So you have actually unique maximum solution. This is this H. Then the solution is strictly increasing bijective NC1, and you can actually write down what I plus of a point P0, P bar is. These are all points Q0, Q bar, which have distance less than this maximal time interval, maximal time of existence of the solution. And Q0 is bigger than this height of the distance. In particular, this is open and push-up holes, which was, for example, not known if you are in a case where your fiber is not a metric space but a Riemannian manifold, and you have this warp product of a continuous Lorentzian manifold. This was also not known. And the height depends only on the distance to P bar. So yeah, and the boundary of I plus is the boundary of J plus. And if X is geodesic, then you actually have that J plus is I plus and the boundary of I plus. So you get that this generalized cone is a Lorentzian pre-length space, and if you put in a little bit more work, then actually you can show that it's a regular, strongly causal Lorentzian length space. So in particular, maximal causal curves have a causal character, and the time separation is intrinsic. And you can now study curvature bounds for this generalized cone. So we can show that if X has curvature bounded below by K, and then you look at the generalized cone of the constant curvature space with constant curvature K, has time-like curvature bounded below by K prime, then the generalized cone has curvature bounded below by K prime. So, and of course, if you want to have curvature bounded above, then you always have to interchange below with above here. And the special case if F is smooth. Yes, so somehow the second condition is somehow a condition on F, even though it's like slightly formulated in an implicit way, but it's actually a condition on F. And you see that if you look at the case where F is smooth, then this generalized cone is of course a smooth Lorentzian manifold. It's just a smooth warp product, and you can easily compute the sectional curvatures. Then this condition here means that F is minus K prime concave. So F double prime minus K prime F is less equal than 0. And if X is curvature bounded below by K, which is given by the supremum of K prime F squared minus F prime squared, then this generalized cone has curvature bounded below by K prime. Yes. For bounded below by, for curvature bounded above, it would be convexity. And so this gives you a direction of having curvature bound on X, and the assumption F gives you curvature bound of generalized cone, but it also works in the other direction if you know. Yeah. Yes, it's positive. Yeah. So you can think about allowing zeros, and for example, if you allow 0 at the beginning, so at one point this is no problem. We just didn't do it, but would be, for example, nice if you have like cosmological applications in mind, then you would want to have zeros. Yeah. So for the other direction, assume that your generalized cone has time-like curvature bounded below by K prime, and the generalized cone over the constant curvature space MK has time-like curvature bounded above by K prime, then you can say that X has curvature bounded below by K. So here you need mixed bound. So you need that Y has time-like curvature bounded below by K prime, and this condition F uses curvature bounded above by K prime, then you can say something about the curvature of X. Because some of the X is again that you only know something about time-like directions, and now you want to say something about the curvature on X. So you need stronger assumptions. And we can use this we're able to establish the first synthetic singularity theorem. So are there incomplete time-like geodesics? As I said, this is Penrose's definition of a singularity in a generalized cone. Yes, this can happen if f goes to 0 at infinite time, meaning I is not the whole real line. And can we deduce properties of f from time-like curvature bounds, which we actually used in the previous theorems implicitly? So if X is a geodesic length space, Y is the generalized cone over X, and I is an interval AB, and F is for now assumed to be smooth. You can extend this to non-smooth F by having these conditions in a barrier sense, but for now assume it's smooth. And Y has time-like curvature bounded below by K. Then you can show that F is minus K concave. And analogously, if you have time-like curvature bounded above by K, then it's minus K convex. And if K is negative, then A is bigger than minus infinity and B is less than plus infinity. Hence, your time separation function is bounded by B minus A, so it's finite. So the generalized cone is time-like geodesically incomplete. And if K is 0, so if your curvature bound is 0 and F is non-constant, then you have that A is finite or B is finite, hence Y is past or future time-like geodesically incomplete. Okay, and I still have time for the last part, which is a recent preprint. It's this joint work with Tobias Beran, where we introduce angles into this theory. And of course, this works by looking at comparison angles, as in the metric case. So you have a Lorentzian pre-length space, K a real number, X, Y, Z, causally related, which have finite time separations and satisfy the time-like size bounds for K. And now, just for simplicity, say that X is less Y and X is less Z. Then you take a comparison triangle in XY in MK, so the constant curvature space MK. Then the K comparison hyperbolic angle at X, denoted like this here, is just the angle in the model space of this triangle at X, which is just given as the area cos hyperbolic of the inner product absolute value here, because this will be negative. Because if these are future directed time-like curves starting at X, this will be negative. So you take the absolute value here. So this gives you a well-defined notion of angle. And if you just use the Minkowski comparison angle, then we just denote it by tilde. And also it proved useful to define a signed angle, because of course now there is always the problem that you keep track of the causal relation. So you have triangles, you have the angles, so you need to keep track where the angle is and how is the orientation of the edges where you look the angle, where you consider the angle. And for that, it proved useful to introduce the signed angle, which makes it then negative or positive depending on the time orientation and where the angle is. I will not use that now because this may be too technical, but let me just mention that using this signed angle, you can then formulate all monotonicity conditions in terms of the signed angle, and this tells you that somehow this is the right quantity and not the unsigned one. Okay, so the main tool, of course, is the Lorentzian law of cosines, which of course was well known before, which gives you then monotonicity in the angles and in the side lengths and vice versa. And then you can also define the angle between future directed time-like curves, alpha, beta, both starting at X, by taking the lim sup of the comparison angles while you approach the vertex. However, now you again need to keep track of that these points here are causally related and satisfy size bounds, but that's always possible because if you have two time-like curves starting at x, then if you take a t here, a beta t here, then of course you can always find then a smaller s such that this is time-like related to this point here. And this is compatible in the smooth case. So if you have a smooth, strongly causal spacetime, a C1, two C1 curves starting at x, then this gives you the usual angle. And then the main result was that now you can actually characterize this triangle comparison by angle comparison, angle monotonicity. I only have here the future version because this is the first step. You have a future and a past version, but then you also have a mixed version because you need to be able to say something about any kind of triangle, and therefore you need to compare the angles on all the vertices. So we say that the space X has future time-like K monotonicity comparison from below. If for all X, this has a neighborhood again such that U is finite and continuous, and any 2 points now can be connected. Any two time-like related points can connect by a time-like maximal time-like curve. So now we really need that the curves are time-like. And if you look at the small time-like triangle in U, and you take 2 points on the side, so Z prime on the side XZ and Y prime on the side XY, such that they are not equal to the vertex, then actually the angle gets bigger if you go to the vertex. So this is monotonicity comparison from below. I will just maybe draw it. So if you have, say, this is your time-like triangle with the time orientation like that. Here you have X, Y, Z. And now you take Z prime here and maybe do it here. Z prime here and here Y prime, and then you have the big angle and you have this small angle. So you look at the comparison triangle of the whole triangle, and you look at the comparison triangle for this small triangle, which gives you 2 comparison triangles, one for the big one and one for the small one. And if you have monotonicity comparison from below, tells you that the angle can only get bigger if you go towards this vertex. And of course, if you have to have monotonicity comparison from above, then you have then the angle can only get smaller if you approach this vertex. And if you have K monotonicity comparison from above, you actually have to require that if Y prime and Z prime are not causal related, then the comparison points are not time-like related in the model space, because this actually follows from the triangle comparison, but here it would not follow just by looking at the angles. So you have to require it, and actually you can show that this is the equivalence, so this is the right condition. So this was like, as I said, this was the future version, but you need to be able to have all combinations, so this gets a little bit combinatorial. But then if you have time-like K monotonicity comparison from below, then this is equivalent to time-like curvature bound below in the sense of triangle comparison. And same thing for curvature bounded above. The only thing you have to have is that you have time-like geodesics, because for the triangle comparison, it was enough to have maximal causal curves, even though if the endpoints are time-like related. But now you need to have at least one time-like geodesic connecting time-like related points, at least locally. But then under this condition, these 2 kind of curvature bounds are equivalent. And this was the main result. And maybe just quickly tell you how it can then define, for example, a tangent cone and exponential map. So for a point X, you can define the space D plus of X as all future-directed time-like geodesics starting at X, defined on some interval 0 epsilon. And you can define a relation tilde on this space by saying that 2 future-directed time-like geodesics are related, alpha, beta, if they have 0 angle, meaning that they have the same direction. And then you get a metric triangle inequality for these angles. So you then can mod out this relation, get the space of time-like directions, and this is actually a metric space. As long as you know that these angles always exist, and the Minkowski cone, which is like the generalized cone, but the warping function is the identity, over the completion of this metric space is the future time-like tangent cone. So this is similar to in metric geometry. This is one way to define the tangent cone in metric geometry. And it's compatible in the sense that if you look at a smooth and strongly causal space-time, then at the tangent cone, the point X is actually isometric to I plus of 0 in n+1 dimensional Minkowski space. So, and then, for example, you can define the exponential map if X is locally uniquely time-like geodesic and has time-like curvature bound below. Then you can define the exponential map on some subset of the tangent cone by just taking a parameter R, so time separation, and a class of directions, and you just evaluate the curve, which is parameterized with respect to tau arc length at R, and this gives you a well-defined map from the subset of the tangent cone to your space. And if you have a little bit more, then it's actually also continuous. And I'm running out of time, so I will not talk about the outlook, but let me just mention that there is still a lot to do, a lot of interesting questions, and I hope some of them will be discussed during this program. Maybe just mention that, of course, these Ricci curvature bounds and Cavalletti-Mondino introduced, they also have a Hawking singularity theorem. So it's very interesting what this implies, especially if you compare this to low regularity singularity theorems where you have distributional curvature bounds. So does it say the same thing, especially like from a physical point of view or not? Is there natural convergence of Lorentzian length spaces which respect these curvature bounds? And also, for example, if you look at this null distance of Saemann and Vega, and what is the relation to the usual Hausdorff measure and dimension using this null distance with the canonical measures and dimensions we introduced for the Lorentzian pre-length spaces. Okay, thank you very much. Here are some references.